Hey everybody, let's go a little bit deeper into covalent bonds and covalent molecules. And let's talk about hybridization and sigma and pi bonding. I'll save the hybridization for a different video, but let's get into sigma and pi bonding. And this is really neat stuff. That really, I would say that this is kind of the tip of the iceberg sort of things that lead into some really neat chemical theories. So let me get rid of my face, and I'd like to tell you guys that I experimented with a black background, so we're going to see how this works. Okay, so sigma and pi bonds, that's a special type of bond that results, both of these are a bond that results when two atoms come together. Now, before we get into the actual sigma and pi bonds, let's talk about hydrogen atoms. Okay, a hydrogen atom, the electron here is floating around in a circular orbital with an s orbital. That's an s orbital. And then if we take hydrogen here, that electron is floating around. When these guys get close together, close enough together, the s orbitals overlap. Okay? When the s orbitals overlap, you end up having something that kind of looks like this, where you have your hydrogen atoms and the electrons, which are part of that bond. Okay, if we're drawing the covalent bond, it looks like this. But those electrons are able to circulate all around here. That overlap of the s orbital is what creates the covalent bond. Okay, covalent, sharing the valence. Okay, and so now it gets really deep here. Because the s orbitals are overlapping, we call that a sigma bond. S orbitals overlap, we call it a sigma bond. Okay, foreshadowing, but I will tell you that, let's see, pi bonds, wait, there's s's and p's. I wonder what happens when p orbitals overlap. So anyways, whenever you have compounds are always bonded together. Molecular compounds are always bonded together. So if it's a covalent bond, no matter what, you're going to have at least a sigma bond. And if you have a compound that has a multiple bond in it, then it's always going to be there, and it's always going to be what I call the first bond. Okay, so that makes a little bit of sense, I guess, but let's move forward here. Okay, and so pi bonds are really present only when you have multiple bonds. Okay, because for something like hydrogen, my example that I just had, remember the s orbitals are the ones that are overlapping, and these electrons can move around however you want them to move around. But there's no p orbitals overlapping. Okay, so there's no pi bonds in this. That's why sigma bonds are single bonds. Okay, that's kind of a mnemonic that I tell people. Sigma bonds are single bonds. It's true, but it's not where sigma comes from. Okay, it's only when we have double bonds, like if we have carbon dioxide. Okay, there is one sigma bond. Okay, and then the other bond is a pi bond. Okay, so this is a sigma bond here, and then this guy would be the pi bond. Okay, so there's always a sigma bond, and if it's a multiple bond, each multiple bond after the first will be the pi bond. Okay, and so you ready for this? This is exactly what's going on here. Okay, so just because I can't draw, that's why I put these pictures in here. I did a pretty good job with my s's overlapping. Remember, the p's are these kind of dumbbell, they call them dumbbell shapes, but they're kind of like teardrops put together, maybe propellers. But when these guys get close together, they overlap. This is called a lobe. Each of these lobes overlap, and what ends up happening is this kind of bends this way, and this kind of bends this way. This P bends this way, and this P bends this way. And so you end up with this funny, like, almost looks like Baymax from that movie. But this is how p orbitals overlap. And when p orbitals overlap, you end up with a pi bond. Okay? So we can take all these crazy compounds, and we can count up sigma and pi bonds. Okay? And so what I'm going to do is I'm going to use, this is the structure of aspirin, acetyl salicylic acid. And let's count sigma bonds. Okay, so this is, let me make sure that I have this. So there's 1, 2, one of these, 3, 4, 5, 6, 7, one of these, 8, one of these, 9, 10, 11, 12, 13, 14, 15, 16. So I count 16, and the symbol for sigma is like a circle with an extra little line because it's a lowercase sigma. You may be familiar with the capital sigma, which is the summation sign in math. The lowercase sigma is what we use here, and it's a little circle with an extended line over it. Okay, but now we have to calculate, or we have to count pi bonds, and it's a lowercase pi, so the lowercase pi has the wiggly top. Okay, so now I'm going to use the black because you'll be able to see it here. So now we have 1, 2, 3, 4. So we have 4 sigma bonds, or pi bonds. Wow. Okay. Now, I would love to go through this whole big structure, but you can see it's a little blurry. I didn't mean for it to be this blurry, but I will tell you that this testosterone, big, yucky, organic molecule, look, there's only 1, 2, I see 2 pi bonds here. The rest, however many other bonds there are, the rest, TR, the rest are sigma bonds. Okay? And so you could go through and count them, but I just think it's like futility to count all those things. But you get the idea. You take something that's really intimidating, and you can really break it down, and you can talk about that. And so remember, sigma bond, and so this idea can relate to how strong bonds are. Sigma bonds are the weakest, and then pi bonds make atoms even stronger. Okay, and so because, I mean, there's a lot of reasons why you could imagine that. Remember, s orbitals overlap, and it's just one overlapping. The p orbitals, when they overlap, they're overlapping in 2 lobes, so that makes it a little stronger here. Okay, and that brings the atoms a little closer together. So hybridization and sigma and pi bonds really tell us a little something about the strength and length of bonds. So that's why sigma and pi bonds are important, and have a great day.